Okay, anybody have any homework questions you want me to go over? So here's what we got going on. So no labs this week. And no school Wednesday through whatever, Saturday, I guess. There's some Saturday classes. And I'm not giving you an assignment for the week. So, yeah, so you can use the time to catch up or relax or whatever. Also, we're scheduled for the lab exam next week, and I still haven't even graded your lab exams. I've been, yeah, that hasn't been good. I need to think about, maybe we'll put that off a couple weeks. I think that's probably what I'm going to do, but I'll put that on D2L, so look for that. I think you can't take the next exam without seeing what the old exam, how that went, so I think that's what I'm going to do. All right. So the new stuff, we're pretty much done with Newton's laws. There's one more thing we have to talk about with Newton's laws. And that is common misconception number 3. So let's review the ones that we've done so far. And what I'm going to give you here is what the truth is, not what people mistakenly think. So the first one was related to the video in the vacuum chamber, that big vacuum building. Do you remember what the common misconception was that we talked about there?
Gravity affects objects.
That's right. So the truth is gravity makes all objects fall with the same acceleration. People often have a very strong intuition that heavier objects fall faster than lighter objects. In some cases that's true, not in all cases, but the reason for it isn't anything to do with gravity. It just has to do with how air resistance affects different things as they move. Then the second one was also related to a video. It was the bullet being fired and being dropped. Do you remember what that one was?
But they won't be the same. But they won't be the same.
Yeah, and so the way, I think I worded that a couple different ways, but the way I like to think of it is really just gravity affects objects the same, no matter what their motion is, you know. Okay, no, let me reword that. An object's motion doesn't affect the gravitational pull on it, or the gravitational force on it. So whether an object's moving or not, it's going to accelerate down toward the ground at the same rate. So now we're on to the third common misconception, and there's no video for this one. So people often think this. In collisions, there's often a winner and a loser. And then the winner applies a larger force to the loser than vice versa. So an example of that would be like a semi-truck hitting a smaller car. You notice that the collision has a much bigger effect on the smaller car than the truck. So people tend to think, okay, the truck's applying a very big force to the car. The car isn't applying a very big force to the truck. But that's not how it works. The truth is, anytime two objects are in contact, and that includes at any instant in a collision, the magnitude of the force on body A by body B is the same as on body B by body A. They apply the exact same magnitude of force to each other. Okay, in fact, that's such an important idea that it's called Newton's third law. And so what happens when a semi-truck hits a small car? Why does the small car accelerate so much and the truck accelerates so little? Yeah.
The truck has more mass.
Yeah, and that's almost always the reason that you see a winner and a loser. It almost always has to do in some way with the mass of the two things. If you apply 1,000 Newton force to something with a lot of mass, it doesn't accelerate very much. If you apply 1,000 Newton force to something without much mass, it accelerates a lot. And so the truck and the car hit each other. The forces that they feel are the same in the opposite directions. But that force, whatever it is, it's some huge force. Let's say 50,000 newtons. If you apply 50,000 newtons to a small car, it accelerates a lot. If you apply a 50,000 newton force to a semi-truck, it doesn't accelerate very much. And that's why one looks like it wins this collision and one looks like it loses this collision. Okay. Newton's third law, the way it's written in Newton's original paper, manuscript thing, book, you've probably heard this phrase before. For every action, there's an equal and opposite reaction. So maybe it's sort of interesting to find out that that's what that phrase refers to that I'm sure you've heard before. But it's not mathematically a very useful way of phrasing it. It's kind of hard to make sense out of that. A more useful way to think about it is like this. If bodies A and B are in contact, the force on body A by body B is negative of the force vector on body B by body A. They have the same magnitude and they're in opposite directions. So that means if two bodies are in contact with each other and you find the force on one of those bodies by the other one, you can just multiply it by a -1 to find the force of the second one by the first one. So we've already used this, although I didn't really stress that it was Newton's third law. We've used this with pushing forces between bodies, where you always use the same variable to represent the contact force when you go to the other body. We've used a version of it with pulling forces. So we've kind of seen it, but I want to do an example that sort of shows how this works. Okay, so let's say that moving along this horizontal surface, that doesn't look very horizontal. Okay, let's say we have 3 of these carts in contact with each other. A 3 kilogram, a 2 kilogram, and a 1 kilogram. And let's say we have a 20 Newton force over here and a 10 Newton force here. And we want to know what's the force vector on body 2, the 2 kilogram thing, by the 1 kilogram thing. Okay. Well, this is one of those problems where you have multiple bodies that have the same acceleration. So we're going to start by isolating the whole thing and calculating the acceleration. So there's what we're isolating. There's a weight force down of 6 times 9.81 is 58.86. Is that right?
Yeah.
Okay. And then an upward force pushing from the ground, I'll call that N total. And then the 20 Newton force over here, and the 10 Newton force over here. And there's nowhere else the surroundings contact the boundary, so that's it. So Newton's second law says 20, 0, plus 0, negative 58.86. plus 0 n total is equal to the mass of the system, 6 kilograms, times the acceleration. I did forget the 10, thank you. So the 10 is in the negative x direction. 1, 2, 3, 4, 1, 2, 3, 4. Okay, so now we have it. 6 times the acceleration. Is this going to move along the x-axis or the y-axis? X, so we'll call this A0. The y equation doesn't, so what we're trying to find is the acceleration vector, this. So we need to solve for A. So the equation that helps us, where did you come from? Hold on. Good Lord. Okay, so the equation that's going to help us is the x equation. It says 20 plus 0 minus 10 is equal to 6a. So 10 is equal to 6a. So a is equal to 1.6 repeating meters per second squared. If you plug that into the acceleration vector, you get an acceleration vector of 1.6 repeating, 0 for y. And if you want to visualize that direction, it's in the positive x direction, so it's this way with a magnitude of 1.6 repeating. Okay, so that's how the whole system is accelerating. Now, in order to find the force applied to the 2 by the 1, we're going to use that acceleration when we isolate an individual body. The first individual body you would think of isolating is the 2 kilogram one. So let's think about that for a second. So what if now we isolated the 2 kilogram? The free body diagram would look like this. We have a weight down of 19.62, a pushing force up of N2. On the left side, we have the force pushing from the 1 kilogram. I'll call that R1. From the right side, we have the force pushing from the 3 kilogram. I'll call that R2. Okay? And so now maybe you see that we wouldn't be able to calculate, like we're trying to calculate this force here. But from isolating the 2 kilogram cart, we wouldn't be able to do that because we have 2 unknown horizontal forces. So we couldn't solve for either one of those. So what are we going to do instead? You know, this circled thing is the force on the 2 by the 1. So instead what I'm going to do is isolate the 1, calculate the force on the 1 by the 2, and then remember force on 2 by 1 is just the negative of that. Okay? So instead, I'm going to isolate the 1. So a free body diagram of the 1 kilogram we have a weight of 1 times 9.81, a pushing force N1, a pushing force from the 2 kilogram on the right side, so that's this way, and that is this R1 here, so that's what I'm going to call this. And this whole force vector here is the force on the 1 by the 2. And I missed the 20. Don't forget to put that 20 Newton force in there. Okay? So now let's go to Newton's second law. We have 20, 0, plus 0, negative 9.81, plus 0 and 1, plus negative R1, 0, is equal to the mass, 1 kilogram, times the acceleration vector that we know now is 1.6 repeating, and then 0 for y. We're trying to calculate this force vector. You know, this force vector here is the force on the 1 by the 2. So we use the x equation. It says 20 plus 0 plus 0 minus R1 is equal to 1.6 repeating. So 18.3 repeating is equal to R1. And so the force on the 1 by the 2, plug that 18.3 repeating into this red circled vector, and you get negative 18.3 repeating 0. Or if you want to visualize that, that's in the negative x direction with a magnitude of 18.3 repeating. Well, Newton's third law then says the force on 2 by 1 is the opposite of this. You know, just multiply this by negative 1 and you get positive 18.3 repeating 0. Or in other words, the same magnitude and the opposite direction. Any questions about that? There's another way you could do this, by the way. You don't have to just isolate the 1 kilogram and recognize Newton's third law applies there. You could also draw a free body diagram of the 2 and 3 together. So that would look like this. There's the 2. There's the 3. The mass of the whole thing is 5, so this would be 49.05. There's a pushing force from the ground I'll call N23. On the 3 kilogram, if we go back up to the top, there's that 10 Newton force. Over on this side, there's the pushing force from the 1 kilogram. Again, that's the one that I've been calling R1. So just in case just so you can tell if you look around what this force represents, I'm going to give it the same name. Newton's second law says R1, 0 plus 0, negative 49.05 plus 0, N23 plus negative 10, 0 is equal to the mass of what we're isolating this time times the acceleration of the system. This vector here is the force on the 2 by the 1. So this force vector is what we're trying to find. You can use the X equation. It says R1 plus 0 minus 10 is equal to 5 times 1.6 repeating. And so that is 8.3 repeating. So R1, if you solve for it, is 18.3 repeating. Plug it into that circled vector, and you get directly that the force on 2 by 1 is equal to 18.3 repeating 0. Or in other words, going in this direction with a magnitude of 18.3 newtons. Okay, so there's a few ways to think about this problem. If you think about it right, they all tell the same story. I think that's why I have this like irrational dislike of, I mean, I hear this all the time, but people say, like, I'll show them something and they'll be like, oh, I overthought this problem, you know? And I think I understand usually what people mean. But I just want to point out that when you get to the point that you're hoping to get to where you just really understand all these concepts, there's no such thing as overthinking it. Every way you think about it tells the same story if you're understanding what's going on. You know what I mean? There's no such thing as like the best way to do physics is to just trust the first thing that pops into your head. As you understand these concepts better and better, you start being able to see that you can do things all these different ways. And the answer you get the second way gives you confidence about the first way you did it. You know what I mean? Anybody have any questions about that? All right. Well, I think we'll get out of here a little early today, but I want to do a couple of problems first. Just I'll write them up here, give you time to work on them together or by yourself, and then I'll go through it and just sort of, we're done with the Newton's laws stuff, so let's just sort of go back and make sure that you're sort of solid on these ideas. Okay, so here's the first one. You have an incline of 20 degrees. and you have a 20 kilogram cart that's connected by a cable and a pulley to a hanging mass of 5 kilograms. What's the acceleration vector of the 5 kilogram mass? So see if you can think your way through this problem. Talk to each other. Feel free to ask me questions if you feel like you're just stuck on one thing and you need a hint or whatever. And then after I give you some time to work on it, I'll go through it and you can sort of check the steps of what you're doing based on what I do. All right, well, this is a problem where the two bodies are connected, but their accelerations are not the same. So the way we're going to approach it is we're going to isolate one of the bodies, come up with an equation we can't solve on its own, then isolate the other body. And the tricky step, remember, is determining how the acceleration of the second body relates to the first one. So I'm going to go through, my first body I'm going to isolate is the 5. That doesn't have to be the case. You'd get the same answer in the end for this vector, for this acceleration vector, if you isolated the other one first. Okay, so free body diagram of the 5. Oh, another important thing on this, before I start filling that in, coordinate systems. When I'm talking about this hanging mass, I'm going to use the usual coordinate system. But when I'm doing my calculations for the rolling cart, I'm going to use a coordinate system for rolling and sliding along inclines. So over here, when I'm talking about the cart, I'm going to be using this coordinate system. And the fact that we're using these two different coordinate systems is fine, okay? Okay, so there's a downward force of 49.05 and an upward pulling force from the cable. I'll call that T. Newton's second law says 0T plus 0, negative 49.05 is equal to the mass times the acceleration. Does this hanging mass move in the X or Y, along the X or Y axis? Y. So I'm going to write this as 0A. And notice I don't know whether this is going to move in the, whether this is going to accelerate in the positive or negative Y direction. But for the first one, you can just always write it as a positive A. The sign is going to work out on its own, okay? All right, well, it's pretty obvious which equation we're going to keep here. The first one just says 0 equals 0. The Y equation says T minus 49.05 is equal to 5A. And I can't solve that because there's two variables in it, but I know I'm going to use it later, so I'm going to set it aside. So that's my equation star. And now I'm going to isolate the cart. There's a weight force down of 196.2. There's a pushing force up, I'll call that N. Not up, I mean, that's sort of not being careful about my words. It's it follows the rules of pushing forces, so it's perpendicular to the surface toward the body. And notice that it's not parallel to the weight force, which is straight down. And then the only other force is the pulling force from the cable. So that's parallel to the cable, away from the body. It's the same cable as before, so give it the same variable name. Now we're going to use this rotated coordinate system. Here's the 270-degree line. The weight force is this. And so the angle between the weight force and the 270 line is the angle of the incline, 20 degrees. And so the angle we want for cosine and sine goes from the positive x-axis all the way around to the vector. So what's that angle?
290.
Yep, 290 degrees. Okay, so we're going to, so now Newton's second law. T is in the negative x direction. N is in the positive y direction. For the weight force, it's 196.2 times the cosine of 290. 196.2 times the sine of 290. And that's equal to the mass of this body, 20 kilograms, times the acceleration. Okay, this is really like the last place that things can go astray on problems like this, or, you know, maybe the trickiest part of these whole problem of problems like this. So now what you want to do is think, if the first body moves in its positive direction, which way does the second body move? Yeah, so if you move the 5 in the positive y direction, the 20 moves in its positive x direction. So I'm going to write this acceleration vector as positive a0. So
Because you chose on the first line diagram to move the acceleration of y and then the positive, it was a little bit.
yeah, so basically what it,
Because you could choose the opposite, right?
yeah, so what it, all that it has to do, the way that you define these directions, is, so now we don't know what A is. It could be positive or 0 or negative. But we know that if it's 0, it's going to be 0. So if we know that the acceleration vector is 0 for the first body, it's 0 for this body. If it turns out that this first body has an acceleration in the positive y direction, the second body is going to have an acceleration in its positive x direction. And if it turns out that our first body has an acceleration in the negative y direction, the second body is going to have an acceleration in the negative x direction. So it's not that we're specifying which direction it's going to accelerate. We're just coming up with a relationship between those two. Okay? Okay, so the x equation here says negative t plus 0 plus 67.10 is equal to 20a. So negative t plus 67.10 is equal to 20a. And that's our second equation that we're going to set aside. And now it's just math, just solving that system of equations. So the system of two equations for two variables is, so we got t minus 49.05 is equal to 5a. and negative t plus 67.10 is equal to 20a. Substitution always works. If you want to be tricky, in this case, you could just add those two equations together and it'll immediately let you solve for a. But I'm just going to keep doing it by substitution because it always works. So this first equation says t is equal to 5a plus 49.05. Now I'll plug that into the second equation. So we got negative t, and in place of t, I'm going to write 5a plus 49.05 plus 67.10 is equal to 20a. Remember, you have to distribute that negative sign through those parentheses. So this is negative 5a minus 49.05 plus 67.10 is equal to 20a. So 18.05 is equal to 25a, and a is equal to positive 0.72 meters per second squared. We were asked for the acceleration vector of that hanging mass. And so this is what we want. All we have to do now is plug in that a value. And so the acceleration of the 5 is equal to 0.72 meters per second squared. Or in other words, it's accelerating in the positive y direction with a magnitude of 0.72. Any questions about that? Okay, let's do one more question. Let's say we have an angle of 30 degrees. And a block on the incline. Let's say this is 10 kilograms. And let's say at this instant, the block is moving up the ramp. And let's say our coefficient of kinetic friction is 0.2. What's the acceleration vector? And is it speeding up or slowing down? Okay, so take a few minutes and see if you can get through this one. Okay, well, remember that we're going to use a coordinate system. Like this. You don't have to do that. You could figure out the directions of all the vectors. It just would take more time, more cosines and sines and stuff. So we're going to do this. Okay? It's just a time saver. You always can use whatever coordinate system you want. But okay, so before I get into the free body diagram, let's think about the weight force vector, because that's the thing that is always going to be a little ugly when we use this rotated coordinate system. So here's the 270-degree line. Here's the weight force of 98.1. This angle between the 270 and the weight force is the angle the incline makes with the horizontal, so that's 30 degrees. And so the angle that we want for cosine and sine goes from the positive x-axis to the vector. And so what's that going to be? 240, yep. And so that weight force is going to be 98.1 times the cosine of 240, 98.1 times the sine of 240, and that comes out to be negative 49.05, negative 84.96. Okay, so the free body diagram now. We have the weight force. We have a pushing force from the ramp. I'll call that N. The friction force is opposite the direction of motion. I said that at this instant, this block is sliding up the ramp. Like, you know, imagine someone gave it a big shove and it's still sliding up the ramp when we do this calculation. So the friction force is going to act down the ramp like this, and its magnitude is the coefficient, 0.2, times that pushing force from the ground, and that's because the friction force gets bigger if these two things are pushed harder together. And so Newton's second law says negative 49.05, negative 84.96, that's the weight force, plus 0n. This 0.2 is in the negative x direction, this 0.2n. So we have negative 0.2n, 0. And that's equal to the mass, 10, times the acceleration. Is this moving along x or y? X. So A0. And for friction problems, you're always going to first use the y equation. So we got negative 84.96 plus n is equal to 0. So n is equal to 84.96. By the way, if you ever get a negative value for that n, something went wrong. It should always be positive the way we're doing it. Now plug that into the x equation. Negative 49.05 minus 0.2 times 84.96 is equal to 10a. And you get negative 66.04 is equal to 10a. So a is equal to negative 6.60. We want the acceleration vector. So plug that value for a into the acceleration vector as we determined it before, and you get negative 6.600 or if you want to visualize the direction, that's in our negative x direction. So down the ramp with a magnitude of 6.60 meters per second squared. Okay, so is this object speeding up or slowing down? Slowing down because the acceleration is in the opposite direction of the velocity. Yep. What do you think would happen to this if I said that there was an additional, I'm going to erase this in a second, but what? Can't read that. What do you think would happen if I said there was an additional force of 100 newtons pushing down that way? What do you think would happen to the friction force? Let's just think about the friction force. Pushing into the, see that little arrow there? Yeah, so what it would do is that would increase the normal force. And then when you calculate that friction force, you'd multiply the bigger normal force to it. And so you'd get a much bigger friction force. Since this is already slowing down with the smaller friction force, it would have a much bigger acceleration slowing it down. You can think of it as it would slow down much more quickly. Okay, so the value of that normal force has a big effect on the acceleration because the friction force depends on how hard that's being mashed into the ground, you know? Okay, that's it. Have a good few days. And I'll put that on D2L that we're not doing the lab test next week. So nothing next week for tests. Then I think our next exam, actual exam, is the week after that, and then we'll do the lab test the week after that. But I'll put all the dates on D2L.
Isn't it there's a total of 3 tests that we have to take for sit-down tests and 3 lab?
There are 4 sit-down exams where you do problems, and there are 3 lab exams.
Okay.